Alright guys, in this video I want to cover an introduction to rational functions, and at the conclusion of this video I'm not sure that you'll be able to necessarily start a homework assignment, but I want to keep this video kind of short and give you all the information that you need leading up to section 5.4 and 5.5. That will, when we cover that, it'll make more sense. So a rational function. And guys, with this, we're going back to rational. Rational, in context of the number systems, just means any number that can be written as a fraction, where the numerator and the denominator are both made up of integers. A rational function, r of x, is of the form r of x equals p of x over q of x. So we're going to see that's very similar to a rational number. But instead of the numerator and denominator being integers, p and q are polynomial functions. So if you take one polynomial function divided by another polynomial function, the result is what we call a rational function. So for example here, if we want to talk about the function, say f of x equals 2x plus 3 over x plus 1. Okay, and we're going to be, in this upcoming sections, working with this algebraically, knowing, given the function, algebraically, being able to take this function and create the graph without the use of technology. But before we jump into that, I want to jump over and show you what this looks like algebraically, or graphically. So I already have it typed into Desmos here, and what you see is we get this kind of a weird hyperbola, almost like shape, where we have two diagonal, borderline, similar to parabolas. They're not parabolas, but that's what they look like. But what we have is, I want to just show you here, at x equals -1, we have what's called an asymptote, which is a line or a value that the function approaches but actually never gets to. So the function never actually exists at -1, but it approaches -1 on both sides. And then we also have another asymptote at y equals 2. So we can see the function, as we go to infinity, approaches y equals 2, but it never actually gets to it. And it does that in both directions. I'm going to just real quickly copy this over to my paper here, and then we're going to discuss all of this in terms of the context of how it's graphed. Alright guys, and I went ahead and copied the picture over to my paper here, so if you need to pause the video, take a minute and draw all of this, and then listen to the description of what's going on in the picture. So we've got this graph of a rational function, and we see that this has a little bit different behavior than what we're used to. First thing I want to go over is what we call asymptotes. We've got two asymptotes here. At x equals -1, we have what's called a vertical asymptote. And so it never gets to -1. The function does not exist, which we should know that because of the function's implied domain. So if you remember going back to implied domain, when we had division by zeros or square roots of negatives, there was excluded values in the domain. So since we're dividing by x plus 1, and x plus 1 cannot equal 0, that means x cannot equal -1. So we know the function's domain is -∞ to -1 union -1 to infinity. And so what we see is at -1 we end up having this vertical asymptote. And we can write that as a kind of similar to an end behavior, but we have an end behavior, or a behavior near the asymptote. So we say as x approaches -1, and guys, this minus sign afterwards means from the left side. So as we get close to equaling -1, but from the left side of -1, f of x approaches -infinity. The function travels down. and as x approaches -1, positive means from the right side. So if we look at the right side of -1, the function approaches infinity. So if we ever have a given value where approaching from the left or right causes a given value on the x-axis where we approaching from the left or the right causes the y values to approach either positive or negative infinity, that's going to be the definition of where a vertical asymptote lies. So now the horizontal asymptote, y equals 2. That is the behavior of the function, and that has to do exactly with in behavior. The horizontal asymptote at y equals 2. If we look at the graph here, as x goes to infinity, the y values approach, so as we go to infinity, the y values approach 2. And as x goes to negative infinity, the y values over here on the left side of the graph approach 2. So what the function's approaching as we go to the ends of the graph, the end behavior of the graph, if these aren't approaching infinity or negative infinity, if it's approaching a specific number, then that's called a horizontal asymptote. Alright, going over just a few more key features here, guys. We have the X-Intercept is at -1.5, 0. And guys, that's the same as always. We're just going to set the function equal to 0 and solve. So if we took this function, let's just go ahead and run through that real quick. If we take the function and set it equal to 0, we see that finding the x-intercept is quite easy. We can times by x plus 1 on both sides. The nice thing about that is the right side, the x plus 1 cancels, and the left side, 0 times anything is 0. And then when we solve 0 equals 2x plus 3, we get x equals -3/2, which as a decimal is -1.5. So the nice thing about finding the x-intercepts is you really just need to set the numerator equal to 0, because you'll always multiply the denominator over, and 0 times everything will always give you 0. Now, and then same with the y-intercept. The y-intercept at 0, 3 is still the same way that we've always done it. Set x equal to 0 and evaluate. And so if I go up here to the function, and I plug 0 into the function, 2 times 0 plus 3 over 0 plus 1, we get 3 over 1, which is 3. Okay, so we know how to find the y-intercepts, we know how to find the x-intercepts. Now our concern is how do we find the vertical asymptotes, and how do we find the horizontal asymptotes, and then how do we know when it's doing this kind of behavior. Okay, so I'm going to add this with pencil, that way I can erase it, but how do we know the graph is doing this versus maybe the graph doing this, or so on and so forth. Okay, so how do we determine that? And that's what this is kind of all leading up to. One thing I want to show you is, we'll just start off with the vertical asymptotes. A lot of times people go, okay, the vertical asymptotes isn't bad. We find the implied domain. The implied domain says, well, the bottom can't be 0. And whatever the excluded values is the location of the vertical asymptotes. Okay? So x equal -1 told us there was a vertical asymptote at -1. Okay? And that is true. However, it doesn't always give us a vertical asymptote. So let me just show you an example. If I jump back over here to Desmos and I clear this out. Okay, let me come in here and type in a polynomial or a rational function. F of x equals, let me do x plus 3 divided by x plus minus 2. Let's do that. So then we see we get a very similar graph, and we can see we do have a vertical asymptote at 2. But let me show you what happens. If I come in here and add another factor of x minus 2 on top, well then the graph turns into a straight line. Almost a straight line. It's not quite. And you might say, well, duh, it turns into a straight line, because if you look at the rational function, the x minus 2's would cancel, and that would leave us with just x plus 3. And if I do that, you can see that the two graphs do indeed fall on top of each other. Okay, but there's a little bit slight difference. So the question becomes, well, why is it when the x minus 2 is on top? Because here's the dilemma. Let me jump back over to my paper real quick. So if I type in the function f of x equals x plus 3, x minus 2 over x minus 2. This reduces to f of x equals x plus 3. But the dilemma is the domain of this graph is negative infinity to 2 to infinity. Because if we set x minus 2 says it can't equal 0, we get that the excluded value is x cannot equal 2. Now, this is not a rational function. We don't have any divisions, so there is no restrictions on the domain. So the domain of this one would be negative infinity to infinity. And now when we go back over here to Desmos, you'll see that. The graph of f of x equals x plus 3 is a line that crosses at 3 with a slope of 1. The graph of f of x equals x plus 3, x minus 2 over x minus 2 crosses at 3, has a slope of 1. But when I go over to 2, there's an open circle in the graph. Okay, and we actually call this a hole in the graph. So if we go back to the graph here, I'm going to just show you this. I'm going to use my trace function with my finger. If I trace this, when we get to 2, look what it is. It tells us that it's 2 comma undefined. And so the hole on Desmos doesn't actually show up unless you do the trace command. So we see that the domain of this graph is negative infinity to 2 and 2 to infinity. Whereas if I come in here and just type in f of x equals x plus 3, and then I do the trace command, at 2 we get that it is not 2 comma undefined, but it's 2 comma 5. So this function does exist at 2, whereas the top function does not. Okay, so we can't always just look at the excluded values, the implied domain, and know if it's an asymptote or a hole. So you have to ask yourself, does the function reduce? Okay, so for example, if I have this function, f of x equals x squared plus 6x plus 8 over x squared, just bear with me for a second, plus x minus 2. So if I go to find the implied domain of this function, I would say x squared plus x minus 2 cannot equal 0, and then this factors to x plus 2, x minus 1 cannot equal 0, which means that x cannot equal negative 2 and x cannot equal 1. Okay, so these are your, we'll call them candidates. Okay, they could be a hole, or they could be a vertical asymptote in the graph. Okay, so the key here is does the function reduce? So I'm going to extend this function out. X squared plus x minus 2. We already know that this factors to x plus 2, x minus 1. But then the top here, the factors of 8 that make 6 are 2 and 4. both positive. And when we do that, the function reduces. The x plus 2's cancel, and this function reduces down to x minus 4 over x minus 1. Okay, so what we see is since we have removed this factor, we've removed x plus 2 when we reduced. What that means is x equals negative 2 is just a hole in the graph. Okay, so that's how we identify that's a hole. Now, here's the thing. X minus 1 is still an excluded value. So after we reduce the function, if it's still an excluded value, then that means if we were to set it equal to 0 and solve, x equals 1 is going to be a vertical asymptote. So that's how we tell the difference between a hole and a vertical asymptote on a rational function. We have to factor the function or reduce it. If the factor gets removed, then that means it's just a hole, but if it does not, it gives us a vertical asymptote. And then if I jump over here to Desmos, just to show you this, let me go in here and type in this rational function, f of x equals, and guys, if you're ever using Desmos, it's important that you put each of these in parentheses. That way when you convert to your division, it puts it all over the fraction. And so when I type this in here, guys, we see that if I type in x equals 1, x equal 1 is indeed a vertical asymptote. And then at negative 2, if I come over here and do my trace command, at negative 2, look what we have. We have negative 2 comma undefined. Okay, so we see that there's a hole in the graph at negative 2 and a vertical asymptote at positive 1, which is what we were able to come to the conclusion of algebraically with the function reduction. Okay, so that's how you determine holes versus vertical asymptotes. And then the last thing I want to cover is how do we determine horizontal asymptotes? Okay, so horizontal asymptotes deal with the function's behavior as x approaches positive or negative infinity. Okay, so really it's just, as we've said in the past, the end behavior. And so let's say we've got the rational function p of x over q of x, where p of x and q of x are both polynomial functions. So since it's a polynomial function, p of x would follow the definition a sub n x to the n power, a sub n minus 1 x to the n minus 1 power, all the way down to a sub 1x plus a sub 0. And let's just do the same notation. Now, we can't use this same definition because it's a different polynomial function. But cube of x, let's say q of x is a sub m x to the m power plus a sub m minus 1 x to the m minus 1 power. And that's going to go all the way down to a sub 1 x plus a sub 0 in context of the rational or the polynomial function q of x. Now, like I just said a second ago, horizontal asymptotes deal with the function's behavior as x goes to positive and negative infinity, and this is just called the end behavior. And when we were doing end behavior of polynomials, we talked about if you want to know the end behavior of each polynomial, you don't need to know every single term in the polynomial. You only need to know the first terms. Okay? Which means we really only need to know the degree and the leading coefficient. But for rational functions, you have to know the degree and the leading coefficient of both the top and the bottom. Okay, so here's how this works. To find the horizontal asymptotes, you compare the degrees N and M of the numerator and the denominator P of X and Q of X. Okay, because that's going to tell you how fast the top and the bottom of the function is growing. And so we've got three cases. Case one. Let's just start off with the easiest one. N is greater than M. So let me throw an example here. Let's say we've got f of x equals 2x squared plus 1 over 3x plus 5. Okay, and in this example, n is the degree on top, which is 2, and m is the degree on the bottom, which is technically 1. And so we see 2 is greater than 1, which means n is greater than m. Okay, and so just like within behavior of polynomial functions, the fact that we're squaring on the top means the top is going to grow much faster than the bottom, because the bottom is just being raised to the first power. So in this case, this is going to be, as we go to infinity, this is going to be an infinity divided by infinity problem. Now, here's the concept of this. If n is bigger than m, meaning the top is growing much faster than the bottom, then this infinity on top has a higher magnitude. It's a larger infinity than one on the bottom. So when you divide these two, you will get an infinite answer. So if n is greater than m, there is no horizontal asymptote. It does not approach a specific value as we go to infinity. And I'm going to jump over here to Desmos and show you. So if I come in here and type in 2x squared plus 1 divided by 3x plus 5, we see that it doesn't approach, and I'm going to bring this graph over to my paper. That way I can talk about it and you can see what I'm pointing at. So we can see here, if we look at the ends of the graph, as x goes to infinity and as x goes to negative infinity, it doesn't approach a single number. The function's unbounded. It goes on forever towards positive infinity and negative infinity. So there's no horizontal asymptote. There's no tapering. Now, what this graph does actually have is it has what's called an oblique asymptote, which is like a slanted line. And it's kind of hard to see, but it follows a pattern of a slanted line. And we'll talk about that more in upcoming videos. But mainly what I want you to get from this is, if the power degree on top is larger than the degree on the bottom, that means there's no horizontal asymptote. Now, case 2 is, what if the degree on top and the degree on the bottom are the exact same? So for example, f of x equals, actually we can go back to that first example we did in the notes. 2x plus 3 over x plus 1. And if we go back to that first example in the notes, guys, and I'm not going to retype it into Desmos, you can look back at your notes. We had this graph. We had a horizontal asymptote. At y equals 2. So once again, we can see here, this is x to the first on top, x to the first and the bottom. So the degree on top, n, is 1. The degree on the bottom, n, is also 1, which means n is n. Okay, so they're both growing. All right. So what's kind of odd about this one is this is saying, well, in this case, it's infinite over infinite as we approach infinity, but when this divides, we get an answer of 2 in this example. That's what the horizontal asymptote is. And the reason being is we're just looking at these leading terms. And we see that this one on top is twice of what's on the bottom. So this will always be 2 times whatever the bottom is. So as we approach infinity, the one on top will always be twice the infinite amount on the bottom. Therefore, it reduces down to 2. Okay, so when the degree on top and the degree on the bottom are the same, the horizontal asymptote is the division of the leading coefficients. And we could even, based on my notation that I have up here at the top, the leading coefficients would be a sub n divided by a sub m. So y equals a sub n divided by a sub m. So in context of this problem here, what we're talking about is when the powers on top are the same, we look at these leading coefficients here. So we see that it's y equals, the leading coefficient on top is 2, the leading coefficient on the bottom would be 1, and 2 divided by 1 does indeed give us 2. Okay, so that's what happens if the degree on top is the same as the degree on the bottom. And then the last case that we're going to cover is, what if the degree on top is smaller than the degree on the bottom? So as an example here, let's say we do 2x plus 1 over x squared plus 6x. And let me just jump over here to Desmos and show you what that looks like, and then we'll talk about it. And so we see that we get some really crazy behavior on this one that we haven't looked at yet. And this is, we got these crazy hyperbola almost like behavior, and then we have this crazy S shape in the middle. And so on this one, what we actually see is we have 2 vertical asymptotes. We've got x equals 0, x equals negative 6. And that should make sense, because if we set the denominator x squared plus 6x equal to 0, that's what we would find. But the big thing from this is, for horizontal asymptotes, is we have a horizontal asymptote at y equals 0. And that's going to happen every single time the degree on top is smaller than the degree on the bottom. So if n is less than m, let me go ahead and just draw this picture real quick. We got something like this. We got a horizontal asymptote at y equals 0. If n is less than m, the horizontal asymptote will always be at y equals 0. And so if we look at this problem here, n is 1, m is 2, the degree on top is smaller than the degree on the bottom. And so what that means is, yes, we're going to be infinity over infinity, but the infinity on the bottom has a much larger magnitude. So we're dividing by a infinitely larger number, which means as this continues to go on forever, this value is going to approach 0. Okay, so the horizontal asymptote is going to be at y equals 0. Okay, and so this is how we identify horizontal asymptotes, vertical asymptotes. We already know how to find x-intercepts, y-intercepts, and how we can determine between vertical asymptotes versus holes in the graph. The only thing we haven't covered in this video is what do we do when we have slant asymptotes. And we'll cover all this in the upcoming video, but this is what we need to have a base understanding of in order for us to move into graphing rational functions, which is what's going to be the upcoming video. Guys, I'm going to post the videos in successive order, so I'm going to label this like rational functions video 1, and then I'll also post, I believe, at least one, maybe 2 more videos of rational functions. And I think it's very important that the first time we watch the videos in that specific order. So I'll get this video uploaded, and then we'll move into graphing rational functions in the next video. Thanks, guys.